Nobody. Oh, one person is out. Krishma. Wait, Krishma, can you hear me?
Yes, Professor, I can
Fantastic.
hear.
Okay, I just wanted to make sure at least one person can hear me. That's good. All right, so it's a two-person class, and we'll see what we're gonna do. So, recording. Oh, it is actually recording. So I'm gonna stop the recording now. Stop recording and restart again. So I know which one to delete. First one. Now I've stopped and start recording. Okay, and I'm gonna share the screen. And then we're gonna what we're going to do today would be essentially going through, let me just make sure that everything is good. It is recording. Okay, so what I'm going to do today is to quickly go through raw pointers, what we've done already. I just wanted to not talk about it, but I guess I am. Wanted to quickly go through raw pointers, kind of remind anybody who's watching and you to kind of remember what it was, and then we're gonna from there move to smart pointers, and if we have time, we're gonna kind of start the introduction about um, start the introduction on smart pointers. So essentially, what we know about pointers, there are they store memory addresses. So essentially, they're variables that store memory addresses, and they allow indirect access to data, which is crucial for algorithms requiring dynamic sizing or efficient iteration, processing variable like data without copying. And the pointers are identified with an asterisk. So essentially, quickly going through it. So a pointer essentially is created by an asterisk added to the type. Therefore, the type and an asterisk together, they mean data. And we use ampersand to extract the data of whatever variable that we have. So essentially, as what we see over here, PTR is a pointer, value is the value pointer pointing to, and so on and so forth. You know this from IPC 144. So that's that. So this is essentially pointer basic. So going forward in OOP345, what we need to now understand about pointers is that pointers are essentially tools to specifically target a piece of memory and traverse through it. So as you see over here, what I have a series of numbers over there, and I'm having the size that is 5, so I know that's the size. Then I create a pointer called start to the beginning of the numbers, and look at the loop that I have over there. So instead of actually saying I want to find the sum of all the stuff over there, instead of actually going through the numbers, I am using the start pointer. Now, pointer arithmetic essentially says when you add an integer to a pointer, what will be added to the value of that pointer is the size of the target, which essentially means when I say start plus I, if start is pointing at 8, then start plus I will essentially be 12 because an integer has size 4, something like that. And the target over there that I have beside the pointer extracts the value of that address. So I'm essentially accessing the pointer via the offset. The index of the array is essentially dictating what the offset is going to be. So running the program just to see what we are dealing with over here. Let me bring this down. Okay. And make this one over here so it's ready. And we need this one as an output. All right. So now we have over here, we have all the good stuff, and it actually finds the sum, which is very fine. We talked about it already. So now take a look at over here. So essentially, number 0 is 10, and address, as you see, that's the address for it. So essentially, I can show you what the value of the number is and what is an actual address over there. And the addresses, as you see over there, they're actually a hexadecimal number. And as it goes forward, you will see that the addresses are added as we are going through. Okay. Now, what I'm going to do over here is this. I think I can do it with a reinterpret cast because that's an address. So let me see if I can actually do it. So I'm going to copy this, Control C, and I'm going to put it over here. So I'm going to do a reinterpret cast to and unsigned long int, and I'm going to put the value over there for the address. Okay. And we're going to run it one more time and see what happens. Okay, so I'm going to bring it over here now and run to cursor, run to the stop sign, and all right. So now let's see what's going to happen in here. So essentially, look at the numbers over there. Now look at the next one, exactly added by 4, exactly added, but it's truncated value of that one is it's smaller. I have to go unsigned long. That's the longest thing that I can go. But anyways, let's continue. As you see, it's essentially every single address is added by 4. Now, alternative way of doing that was to actually, instead of adding I to the start, I can set the pointer to the beginning, do the target. At any time I add 1 to the pointer, automatically it's going to go to the next one, and therefore it does the same thing. The difference is that over here, PTR will be pointing to the last element of the array when we are done, but here start remains the beginning. So this is essentially pointer arithmetic that we went through. Again, a quick review of it. So this will be pointer arithmetic.
What is it called?
Pointer arithmetic, essentially doing math with pointers.
Yeah.
Okay. So that's that. Now, dynamic memory allocation, we know all about it. We have gone through it so many times. Again, I'm just talking about it so we know. So now, kind of, before I go to smart pointers, I want to talk about all these things. So we put it out of the way. So the only difference over here with this one and the other one is that the other one had a statically allocated array, and this is one dynamically allocated array. So the dynamic array is the size that we have. Now, one of the mistakes that people make is sometimes they change the value of the dynamic array pointer over there. If you do that, then you're going to lose. Don't do that. Keep that value, the dynamic array. If you do dynamic array plus plus, it will advance to the next one, but you lose where your array was. Be careful. Anyway, so as you see over here, I am getting the values one by one and put it in an array. Now I can actually use pointer arithmetic to go through the array exactly like the other one to find the maximum value. So thing that I've done over there, please walk through it at home. I'm not going to do it now. and I find the maximum value, but the key is that at the end, I have to delete the dynamic memory allocation and set it to null. This is the, of course, it's gonna end over here. We really don't need to do it, but remember that any pointer that we have to point it to unused, we have to actually set it to null. So, avoiding dangling pointer. Dangling pointer essentially means a pointer that has some value in it, but no memory is set to that address, and that's dangling pointer, which we don't want. Okay, so this essentially is a dynamic pointer. After that, going through compound types. I have over here a structure called course that has title and a grade. Now what I can do over here, have a course pointer, courses, new courses, whatever. So I'm creating a dynamic array of structures, the exact same thing like the other one. So I can start getting the values one by one for the course and set everything over there. Then exactly like the other one, I can have a pointer that points to the beginning of the array of courses, and through the arrow operator, I can access the internals of that composite type using the pointer that is pointing to. So essentially, it's the same, just showing, reminding you that it is now working with a compound type, and at the end, I'm going to delete the courses and set the courses to null PTR. We're good down to this point. Hopefully, this is a quick, refreshing kind of refresher on all the things that we know about pointers. Okay. So this one is going to be struct pointers. And last but not least, talking about, give me a second. Okay, here it is. Talking about pointer to pointer, something that freaks everybody up. And I had a piece of code for it, but I cannot find it, so I have to write it from scratch. No, we don't have it. Okay, doesn't matter. Let's write it. First of all, let's understand what pointer to pointers are. But when I say pointer to a pointer, what does it mean? An easy way to understand is first is what, remember ragged pointers? You know what ragged arrays, you know what a ragged array is? I think we had it in OOP345. Ragged, okay, so the array, when you have a two-dimensional array, essentially when you have a two-dimensional array, you have a width and a height. You have columns and number of columns and the number of the arrays that you have. You can have 3 arrays of 10 integers. It's something like that. Now, ragged array doesn't work that way. So, like, if I want to have, I'm going to write it first in an easy way, then I'm going to go a little bit more tough about it. So, if I write over here something like integer pointer ARR, and I'm gonna put over here something, let's say 3, okay? And I'll say ARR 0 is set to new int 10. Then ARR 1 is set to new int 20. And ARR 2 is set to new int 30. Good? Now to this point. Okay? Okay, now if I have something like this, this is essentially a two-dimensional array. But the difference is that unlike a two-dimensional array that we had, which essentially was something like this. You had a two-dimensional array like this, and each array was exactly the same length. So this is 0, and then 1, and then 2, and then 3, and then, so you had something like this. Now this array is actually like this. So you have 3 pointers. The first one, so these are your 3 pointers, 0, and 1 and 2, and the first one has 10 integers, the second one has 20 integers, and the third one has 30 integers. So as you see, it's not rectangular, okay? So this is essentially kind of a ragged array that we have, which means each element has its own size. Obviously, it's a horrible thing to do unless you have some constant values over here, otherwise you're gonna lose track of which one has what size. And then, unlike two-dimensional arrays that are essentially a simulation, this is really a two-dimensional array. When I say a two-dimensional array being simulation, this is what I mean. So if I have something like this, integer a, 3, and 4. That's 1, that's 2, and that's 3, right? I'm initializing it. Now in here, I will have something like 1, 2, and 3. Now in here, I'm going to have 10, 20, 30. In here, I'm going to have 100, and 200, and 300. Okay? Now, if I actually create a pointer to the beginning of this array, so essentially that A of mine is an address holding the address of this two-dimensional array. If I actually do something like this, I'm going to say int pointer ptr is sent to reinterpret cast to an integer pointer from A, right? So I'm essentially setting A to that, okay? If I have something like this, cout ptr 0, what's going to get printed over there? 1, the first element, right? So the other, now those new thingies are going to cause leaks, so I'm going to just do it like that. Now, if I run it, what I'm going to have over here is going to be 1, right? The first element. Now, if I have over here,
Sorry, Professor.
yes.
I just have one doubt.
Pardon me?
Shouldn't PTR?
Oh, wait. Give me a second. Give me a second.
Yeah.
Go ahead, because the audio was low. I couldn't hear it. One more time. Go ahead.
I was just wondering, shouldn't PTR 0 point to the entire first row of elements, like 1, 2, 3?
No, that's the thing. again, let's bring that thing back. So I put a little bit too many of this. Let's say I'm talking about the first three, okay? So let's say this is the array that I drew over there, okay? So essentially this becomes 0, and this 1, and this 2, right? And then each one of these, it has an element over here. So I'm going to go, sorry, for some reason. There we go. So I'm going to have over here, this is 1, this is 2, and this is 3, and 4. Oh, and by the way, I made a huge boo-boo over there that I have to fix immediately, which is here. I forgot to put the 4 over here because these are all 4 and 40, because I had 0 at the end. I didn't want 0 at the end. So 400. So now in here, I have 1. In here, I have 2. In here, I have 3. And here, I have 4. And here, I have 10. Here, I have 20, and so far, so on and so forth. Are we good with this? Now,
Yes,
now this A essentially points to here, correct? Which means A0 becomes the address of the first one, and then A01 becomes 1, A02 becomes 2. Are we clear on that?
So the
Yes.
3 is like the number of rows, and the 4 is the number of.
Yeah, two-dimensional array. Yeah.
Okay.
Wait, so now, but because A is a two-dimensional array, A0 points to the beginning. A1, essentially, when you say A01, the second one over here, the one that is, I'm talking about this one actually, this index, okay? If you add 1 to that index, it adds 3 integers to the address. That's why, sorry, my apologies, control that. I put the circle around the wrong thing. This one, when I add 1 to it, it adds 4 integers. Do we understand that? So when I say A1, it jumps to the second row. Does that make sense? Keep your microphone on.
Professor.
Okay, beautiful. But this integer over here, this one, is a one-dimensional array, not 2. So when I point it to the beginning, it's just a regular array. Therefore, it points to the very first element. So in other words, this would be the exact same thing as Oh, 0, 0. Got it? Now.
Yep.
Because of repeated tests, right?
Yes, because of reason. So they both point to the same place of memory, but the one that you're looking for, that with an A, it's pointing to a compound type of 4 integers. So A0 is first 4 integers. A1 is second 4 integers. A2 is third 4 integers. And I'm going to tell you exactly what is it going to be in the next thing. But here, in that PTR that I have, points to the very first element. Now, I have a question. Who was the person asked, Krishma? Was it you?
Yes, Professor.
Yeah, so my question is that why you are saying it will point to the entire thing. It is pointing to the entire thing. It's an address. But when I put an index in front of it, I'm going to say content of what you are pointing to. So in that, with certain respect, your question is perfectly correct. PTR over here and A, they are both pointing to the same location of memory. And they are essentially pointing to the first row of the array, as you said. But when I put this one, which essentially means this, I could say target of PTR, and I remove this one, and I say target of A0. When I run this, we'll see that they are all exactly the same. They are all ones because they are all pointing to the very first element of this two-dimensional array. Do I make sense?
Yes, Professor.
Okay. Now, my point comes when I do this. So essentially, if I do this, and I run this, now I'm going to have over there 3 shown. Are we okay with this? Now my question is this. What happens if I do this? PTR 5. Take a look at this.
It shows 10.
It will show 10 because there is no two-dimensional array. This is essentially one straight array that is broken down in chunks of 4 integers at a time. So the two-dimensional array is a fake thing. What it does essentially, it creates pointers to compound types of the width of the array. So essentially 1, 2, 3, 4 that you see over there, it becomes one structure of an array of 4, and the first pointer is pointing to that one, and so on and so forth. Do I make sense? Hopefully. And because of that fact, even if you do this, I know it sounds a little nuts. If I say CIA 0 and 5, there is no segmentation fault or anything like this over here. When I actually do this, they all print, the last two will print 20 anyways. Actually went 20. So 0, 1, 2, 3, 4, 5. 5 is 20, not 10. But anyways, so they all go to the next row. As you see, it is actually they put the mechanism in there to kind of tell you, hey, that you're actually, do you see that green line thingy over there? It tells you, hey, you're going invalid data from A0. But because we know that after A0 is A1, it's going to go to the next one, okay? So I just wanted to tell you what the nature of arrays were. So this is essentially what arrays are. Two-dimensional arrays are really a one-dimensional array. So in here, I'm going to say DE.
The pointer.
Too long, are actually one-dimensional. Okay? Yes.
So for PTR that we created, it's storing the memory address of the
Beginning of, yeah.
and then we're dereferencing them. We're extracting the value. However, with the PTR and the index, you can't do 2 indexes, right?
No, that's the thing. Yes,
So
thank you. So PTR cannot accept two-dimensional array because PTR points to one integer where A is pointing to 4 integers. Okay? Which brings me to the next thing. Okay? So keep this in mind. And now let's go back in here. Now in here, I am removing the second element, and therefore the array doesn't know what is that. Like it literally, these are 3 integer pointers. I don't have one pointer with the width of 4, okay? I can go even further and do something like this. Integer pointer, pointer, p equals to new, integer pointer, say 4. Now I have 4 integer pointers, okay? Now I can do the exact same thing as the top one. I can say P0 is, I'm just going to bring it down. So essentially this is P. And I can have the other one. So now that is a fully two-dimensional ragged array. I can even go more bananas and I'm afraid to show that. Each of these is a pointer pointing to an array of integers. We're okay with that, right? I have an array of pointer to pointers, they are called. Okay? So I can even go three-dimensional. I'm not going to write the code. Because in three-dimensional, I can now create an array of three-dimensional, so essentially create a dynamic RAD cube, not a cube. You know what I mean? Okay? So, but I don't want to go there. So essentially, pointers have a recursive type of definition, which means the definition of a pointer is within itself. Just remember that the asterisk that you're adding belongs to the type, not to the pointer. Okay? And pointer to pointers can be described as this too. So essentially, say so in here I'm going to say pointer to pointers. Oh, and something that I had to do. Yes. So to delete the memories of all these things, I have to go for integer I, set to 0 and I less than 3, and I plus plus, and delete ARRI. Okay, to delete all the array. And for P, I have to do for okay, and then I have to say delete P itself. Okay, so essentially first I'm deleting each array, and then I'm going to delete the array of pointers.
Set any of them to null?
Pardon me?
We set anything to null?
Yeah, of course. If I want to use it, I'm going to set every single. Yeah, sure, but yeah, but because the program's ending, I'm just showing that this is how the deletion is going to happen. So remember, when you have a pointer to pointer, that's what you need to do. Okay, what did I do? Okay. So this is pointer to pointer, version 1. And the next version is going to be this. So just to understand exactly what pointer to pointers are, let's do something like this. So if I have over here integer a 3, that I'm going to set it to 10, 20, and 30. Okay? Now, if I have over here integer pointer PTR set to A, okay? Now, if I want to advance PTR to go to the second element, I have to go plus plus PTR, and therefore, what I want to do over here, I want to say C out target of PTR, and it's gonna, we know what it's gonna do. Yeah, there's no, so I'm gonna run it. We know what's gonna happen. It's just gonna show 20 over there. Are we good with this? Like, it's very simple and straightforward thing. I'm gonna show 20. We good? Okay. Now, if I have over here a function, and I'm going to call it advance, and I want to pass this pointer and modify it by 1, what do I do? If I write over here integer pointer P, and I use my C knowledge, and I go, okay, I'm going to go target of P plus plus. So this is what you do, right, when you want to add the target, right? Okay, so now if I actually say, and this is void, by the way. So, and I'm going to also do one line over here. And I'm going to say over here, advance PTR. Okay? And then I'm going to go see out address, target of PTR and NL. So what is the output of the second one? 11. The first one was 20. How did you go to 11? 21. It's going to be 21. I thought that I could, so if I actually run this, it's going to be 21. So what happens, it did not advance the pointer. I wanted the pointer to go to the next one. You follow what I'm saying? If I want the pointer to go to the next one, I need to get a pointer to a pointer and pass the address of the pointer in there. Now it will advance it by 1. Yes?
Can we use pointer reference?
Yeah, of course we can. I'm talking about pointers. This is not C++. What are talking about? Of course, I could have used a pointer reference and be done with it. If I just put a reference beside that thing, yeah, I know that, but we don't want to do that. I want to use only pointer. That's what pointer to pointers are exactly are. Essentially, they point to another pointer. That's it. There's no magic mystery behind it. To do that using a pointer, I have to treat this like a regular variable, pass it to the address, pass the address to a pointer, and then now if you run this, this is a beautiful walkthrough with one answer to see if you actually get it or not. You follow? So you know what's going on, right? Yes.
Yeah, just ask the pointer to a point P is a pointer to a pointer, so it points to A directly.
It should point to another variable. So a pointer points to a variable, right? Now, if that variable happens to be a pointer, what do you call it? Pointer to a pointer. And there's no magic missing. But as soon as you put 2 asterisks, everybody freaks out. That's not the case, just a pointer, for heaven's sake. And then, yeah. And I can go even more nuts. Now I can actually say, what if I want to call another advance in here and modify P? Then you have to have a pointer to a pointer to a pointer. You follow what I'm saying? So if I want to have another advance over here, void advance 2. And in here, I'm going to have integer pointer. I'm going to put a P over here, and I'm going to have the exact same thing. There's no, and I can just, I'm not going to do that.
Well, do you use pointer P or?
Yeah, and then you pass the address of this one to that, and it works the exact same.
Okay, yeah.
Okay, okay, but I don't want to do that because no crazy person does it, but just letting you know that you can infinitely go up, okay? Okay.
But then can we use, I guess, asterisk ampersand?
Yeah, of course. That's why you asked. Can you just use a reference and get over with it? Yes, you can. That's why we learn references. We can, but if it's C, you can't. If you're in C, like you have a C compiler, then you need to know this. And it's hence the raw pointer thing. I didn't talk about references. I said this is raw pointers that we are. So raw pointers are reviewed. We know exactly what they are. Life is beautiful, and we're done with that. We're good at this point. Okay. Now the next thing I want to do over here with that, what shall we call it? Let me just. So what is the problem with pointers? Problem with pointers in dynamic memory is that when you have a pointer and the pointer is pointing to a location, the problem is that you have to always remember to delete the damn thing. Otherwise, you'll be in trouble. Right? How can we fix this problem? Yeah. But how do they do it? Is it magic? Like what happens? So, oh, not resources. Actually, you know what? Let's have a break. I'm going to let's resume this one. Okay, Krishma, I'm back. All right, so we're going to go to continue recording, start recording. All right. Okay, so make sure the audio is being recorded. All right, so next thing we need to do over here to see how we can actually fix these problems with pointers not forgetting doing things. So this is what I'm going to do. Take a look. I'm just going to create a header file. I'm going to add a new header file, new item. Where is it? The header file. And I'm going to call it unptr.cpp, .h, actually unptr.h. Okay. And obviously for this unptr, we're going to have the stuff that we need to have for our header files, which is essentially adding the namespace and the things we need to have. So anyways, so I'm going to create a template for a class. So I'm going to create a template. Type name, type. And I'm going to create a class and I'm going to call it a unique pointer. Okay. So a unique pointer class of mine job is to replace a pointer. So I want to create a template to impersonate or simulate a pointer. To do something like that, the very first thing I need to have over there as a property is essentially a type to a pointer that I want to create. So that PTR, the pointer thingy. Right off the bat, I solve the problem of pointers being set to null. So immediately, as soon as this is created, it's going to set the pointer to null. So the problem with setting the pointers to null when you create it, it's gone. Okay? Now, the next thing, I'm going to create a constructor for it. And in this constructor, I'm going to have a type pointer, PTR pass, so what I want to initialize it. And if they don't put anything, I'm going to put a null pointer. Of course, null pointer is going to be the thing. And then I'm going to set the MPTR to the PTR that I'm receiving. Okay? Simple and straightforward. So that's my one argument constructor or no argument constructor if I want. So that's good. The next thing I need to do over here, give me a second. So what I'm going to do, I'm going to go to main and prepare something in main so we can actually kind of relate to what we are doing in here. Give me a second. So I'm going to have some kind of a compound type created. So I have an employee, usual stuff with the operator set to display it and printing stuff. So very simple things. And then what I'm going to do over here is create an instance out of this in my main using my unique pointer. Okay, so essentially the pointer that I created over here, satisfies that syntax. So I'm going to say create unique pointer for an employee called P that holds the address of a new employee. Good? All right. All right, so let's continue. Now, the next thing I need to do over here is to make sure this pointer cannot be copied, because I want this pointer to point that piece of memory and nothing else, to make sure that two pointers don't point to the same piece of memory. Okay? If I want to do that, how can I actually do it? Simple. Delete them. Delete the copy construction, delete the copy assignment. So no one can make a copy of my pointer. But if they move it, which means if one unique pointer takes over another unique pointer and leave the other one behind, I'm in a good position, right? So for that, what do I need to do? What I need to do is essentially move those things around, right? So, and for moving, it's quite simple and straightforward too. We know all these syntax. I'm not going to write it down. I'm just going to go, explain it to you what they are. So when it's copying, my unique pointer is not pointing to anything, right? So all I need to do is to make my pointer to point to the other one and make the other one not. Done. So I took over, so the new pointer that I have will take over ownership of the other one. Now, if my pointer is already pointing to something, I don't want any leaked memory. So what do? First of all, I do the usual things that I have. So I get the unique pointer move reference over there, and I'm going to compare, make sure that it's not the same. Then I'm going to say delete whatever I have to make sure that I don't have any memory leak happening again. And what do? I simply do the exact same thing that I did in copy. So first I delete my own, and I'm going to say point to the other one. Therefore, my unique pointer is impossible to be able to be pointed, be set to another pointer and have any trouble with two pointers pointing at a place, forgetting to delete a memory of a pointer before you start. All those things are gone, okay? Now, the only thing is that I want to make sure that this thing acts like a pointer. So when you are saying target of beforehand, so if I say over here, target, if I say over here something like C out target of P, I want this to be treated as a reference of an employee. To do that, what do? We've learned this a long time ago. We just overload the operator for it. Voila. So I'm saying the unary operator target of returns the target of a PTR. And what does it return? A reference of a type. Done. Okay, so that problem is solved. Now, what if the pointer is pointing to, if I want to use the arrow from the key to access, I don't know, employee number or something, I don't know. I want to do like, but what if I want to do this? See out P salary. I want to print the salary. What if I want to do that? So again, no problem. If that operator is invoked, I'm going to return an address first, and the address I'm returning is the pointer. Yeah. So now it's really acting like a pointer. Also, what if somebody wants to see what is an actual address inside that thing? Where is it in memory? I want to have that. If I want to have something like that, again, I have learned all these things from OOP345. Actually, this could be a very good assignment for OOP345 because you have all the information that you want. I can simply overload the typecast constant point pointer, void pointer, and make it a const, and return the address out. So if you want to know what is the physical address in memory, you have that one too. And the most important thing is,
Okay, wait, how does this last function work?
pardon me, this one?
The operator const void.
So if somebody casts the pointer to a void pointer, they can actually receive the actual address in there. So it says if the unique pointer of mine is casted to a constant constant void pointer, return the address out. Yeah, if you want to, because it's void, you don't need to cast anything. Otherwise, I would have casted the MPTR to a void, but any pointer can be casted to a void, right? So essentially I can do this. I can say over here, see out, employee is at const void pointer P. So it actually shows me where the employee is at, in memory, if I want to. And the most important thing again is that I do not want to forget deleting anything. And that's what it is. So I'm going to say when the unique pointer goes out of the thing, delete it. So that's it. This code does not need deleting, and this pointer can be used like a pointer anyway. Right? So if I actually run this, so that creates the pointer. So it creates a new employee with that information. So the employee is created with all the good stuff it's supposed to dynamically. Now it goes in here and actually sets the PTR to that. So the PTR, the pointer that you have over there actually holds the employee. So this actually MPTR is the employee, as you see. Okay? Now in here, I'm going to say target of P. It goes to the operator overload and returns target of MPTR. Exactly what I want as a reference. So it goes back in and the printout happens. Now I want to find out what's the salary, so I need to use the arrow. So it goes to the arrow, returns the address, and therefore I have access to salary. And at the end, I can see exactly where the employee is sitting in memory. And at the end, I do not need to worry about deleting it because it's going to delete the employee right at the end. And I'm done. So this is called a smart pointer. It's called a unique pointer. So unique pointer is like this. Unique pointers, with what I created, you know exactly what it does. You know that a unique pointer, I don't think, because this is recording. The microphone is here. I have to stand in front of this. This microphone is not working for that for some reason. Anyway, so what I'm saying is that the unique pointer that we have over here, its job is to only point at one location. That's why they call it unique. Two unique pointers cannot point at the same time, and so on. So we good with this? Okay. So this is my unique pointer. I'm gonna, we have it over here. Oh, let me rename that. Do you think it's gonna rename it when I just change the? Yes, it did. Yay. Okay, so unique PTR, that's the one. Now, let's create another one that's called the shared pointer. Is this how we called it? Yes, shared pointer.h. So for the shared pointer thingy, I'm just gonna cut to the chase and put everything over here. So you see what's going on. So shared pointers are a bit different. Shared pointers, they say 5 pointers can point to the same location. There's no problem with it. So the code is a bit more complicated. Walk through it later on and see how it works. So for a shared pointer, what it does, it says if 5 things are pointing at the same place, only when all the pointers are gone, delete. Which means the shared pointer needs to keep track of how many pointers, is this type of pointer pointing to the same location or not. So that's why we create not only at line 6 we are creating an MPTR that is a pointer to the type that we want to point to, but also we create a counter of type size t that is like it's a dynamic one because I want to find 2 things. First of all, am I pointing to 2 different things at all, being null or not? Or if it has a value, it is actually allocated, it means there are many things. So I have to count how many things I'm doing. And instead of deleting, I have a wipeout mechanism. What wipeout does, it checks to see if the counter exists. If the counter exists, it reduces it by 1. If the value is 0 or it's not, it deletes both of them. So this guarantees if I call wipeout at the proper place, if there is any other shared pointer pointing to the same location, because the counter is 1, it just reduces the number. It means 1 less. I don't need to delete yet. But as soon as it detects, as soon as it's the last one, then it's going to delete. So what the constructor does, it sets the pointer to whatever it is because it has to. There's no problem with that. Then as soon as the constructor happens, it creates a new instance of the PTR counter to a new size t. Now, if the pointer that you have over here, okay, you see that? If it's not null, if the PTR that is coming in is not null, it adds 1. If it's null, it makes it 0. Because if it's null, it means I'm not pointing to anywhere, right? Okay? There is nothing to point to. But if the pointer is actually pointing to something, then it means now I have one pointer pointing to that object. When a copy constructor happens, I set everything over here. As you see, when a copy constructor is, which means now I'm copying it, it's going to say, okay, first I'm going to point to the same place. I'm going to make sure that my MPTR is the same as the other one. They are pointing to the same place. So the counters are all shared between all the pointers. So one, so I'm going to point to the same place, then I'm going to add one to it. So I'm kind of creating, I'm simulating, like you said static, right? Yeah, but I can't use static because static is shared with all instances of shared pointer. I want to have a common counter only for those classes that point to the same location.
Oh, so you have like two shared pointers, they're gonna have two different.
Two different counters, yeah. So the shared pointers, depending on what they are pointing to, they might have different. So for each memory they are pointing to, they have a counter. Okay? Same thing happens over here for copy assignment. So the very first thing that I'm going to do, I'm going to say wipe out. I'm not going to say delete. Wipe out means wipe out already existing data. If I have anything, wipe it out because I'm being assigned to something. Now, wipe out, if I'm the last one, it deletes. Remember what the wipeout did. Wipeout only deletes the resources if I am the last instance. So I'm using wipeout instead of standard delete. It's a conditional delete. So I'm saying wipe out everything, okay? What if there is already existing data, if wipeout already existing data conditionally, and then I'll go with the rest. So I'm going to set the shared address, make sure they are sharing the same pointer, and then add one. If the object that I have is actually pointing to something, if it's not null, add one to the counter. Otherwise, I'm zero. Moving is easy. You're moving, right? So if you are copying a shared pointer, you are doing a move constructor. It means what I have right now is brand new. Therefore, I'm just going to move the other one here. I'm replacing another one. So if that's 1, I'm going to be 1. If that's 10, I'm going to be, it doesn't matter. Whatever it is. So I'm just moving one to another. So nothing, it's a very normal move. But for assignment, again, I'm using wipeout instead of delete. So what I'm saying, if I'm being assigned to a dying object, okay, what I will do first, I'm going to wipe out, okay, then I'm going to get the values from the other one, and so on and so forth. So it works the exact same way. Like, yes.
Just a thought with all the shared pointers, if the count is add 1 and we're doing a move assignment,
It reduces it.
it reduces it by 1, right?
Yes.
And then it goes to 0, right?
It goes to 0 if it was a last one. Let's say you have 10 shared pointers pointing to a same location,
right.
And you are move assigning one out of it.
Okay.
So it's the wipeout is going to make it 9.
Oh, okay. So
Only the one that is pointing will be moved somewhere else.
Gotcha. Okay.
You follow what I'm saying? Okay. So, and that's that. So the good thing is that, like in here, you can actually see how many things this shared pointer is pointing to. So like how many pointers exist out there, you can simply see what is the count. And obviously, if the count is null, then you have to have a size be 0, return, otherwise you return the content of the thing. Very, very easy. The operator and that one is the same. This we don't need. And the rest is same. So the constructor simply wipes out. So essentially I'm using wipeout for the, yes.
What happens if we, because this, the shared pointer works because when you want to create a new shared pointer, you use the copy constructor, right?
Yes.
So
Either copy constructor or you're moving something into it.
that's what they can point to the same address, right?
Mm-hmm.
And it's all safe. But what if you construct two different objects using the same pointer?
You can't.
No, you,
Look, think about your finger. How many things you can point at the same time?
no, like,
You cannot point to two things with one pointer. Don't confuse yourself. I am using many, it's like 5 people pointing at the same place. You can
yeah,
do
no,
that. So that's what the share pointer is. You just talked about the exact opposite.
no, because like, if you had like a pointer P, and then you create like 2 shared pointers
Mhm.
using the constructor, the one argument constructor.
Yes.
Using the same.
Fantastic. So you have 2 shared pointers pointing to 2 different things at the same time. 2 shared pointers to integers, each one pointing to a separate integer.
But it's using it's constructed out of the same same P though.
No. Oh, if it's, that's easy. Oh, wait a minute. So I have shared pointer A that creates a new integer.
Out of P, yeah.
No, out of itself, the original. This is number A is the original shared pointer that I have that points to an integer. So I have one shared pointer pointing to an integer. Okay. Now there are 2 scenarios. I'm creating pointer B. When I create the pointer B, either I am setting it to a new integer or I'm copying the other one. Which one do you want?
The right way is copy from the shared pointer.
Okay. What is the wrong way?
Like,
Or the questionable way?
or like you could create another shared pointer out
Fantastic. So I create another, so when you say you create another shared pointer out of what?
of the one that creates A.
How can you do that?
Like I don't know how to explain it. Can you go out to like the one argument constructor?
Okay. Okay.
Like it takes a pointer, right? To create the shared pointer.
Uh-huh.
What if you create 2 shared pointers using the same PTR?
You can't because you're using new inside. This is only supposed to point to a dynamic memory.
Yeah.
So when it's dynamic memory, the only way to get the address of is through the shared pointer itself. And that causes a move or a copy.
But move is only if the type at right side is a shared pointer, right? What if the type at right side is not a shared pointer but just a pointer?
Then you don't do that.
Yeah, so it's
You use shared pointers with shared pointers.
yeah, so that's
Yeah, that's it. Don't forget, these replace pointers.
yeah, I know, but like
Yeah, you're
You
saying,
could-
what if I
you
have
could
an
do that.
integer and I put the address of the 2 integers in one, then it can check the same address, right? If they're
like forget it.
okay, okay, but create the problem.
Yeah.
Create the problem and let me know. Okay. Okay, so
Because it's like if you like there's no point doing that. I'm just
yeah, okay, so sure, but I love to hear about it. Create the problem in the code and let me know. So that's that. So talking about, so whatever I created over here already exists. Okay, so save it. So I'm going to call this, oh, that's that one. One thing I want you to realize and appreciate that what I created is my try to show you what shared pointers are. Don't look at my implementation as what unique pointers are in C++. Read the description of what unique pointers are. They're much more complicated than this. This is making it extremely easy to understand what is it supposed to do. This is not the source code of the C++ library. Do you follow that? Okay, does that answer your question? Okay, sometimes that's the confusion. I'm trying to, this explains what is the
like
base
how it
of
works.
what is the philosophy of it, and then we'll read the instruction. We read actually the documentation of C++ library. I mean, okay, this is my attempt to teach the damn thing. Let's put it that way, okay? So yes, so unique pointers, they are smart pointers. They represent exclusive ownership of dynamically memory allocated object, and that's extremely important. Dynamically allocated object. So unique pointer is designed for that. Unique pointer is not to carry data, carry addresses around. For that, you use a pointer. Okay? For that, we have pointers. If I want to pass address from one place to another, I'm not crazy to use a smart pointer. Smart pointer is to be applied to dynamic memory. Got it? Okay. That kind of answers your question, because you were saying, what if I think what you mean is that instead of a new statement in there, what if I have address of I?
No, I meant like, what if you do line 30 but 2 times?
Line 30. Then you have two different objects.
Yeah, pointing to the same thing, right?
No,
No?
two separate objects.
Oh, right, because it's new.
Yes.
Oh, I was like,
Okay, so you follow what I'm saying?
yeah.
Okay. Okay.
Well, but what
They are two separate objects, but with identical content, man. So if I repeat this stay line twice, I have two pointers that are identical. But if there are two things possible, either I do this. Let me just write it down and put you out of your misery. Okay. First of all, this is unique pointer. I cannot copy it. Okay.
yeah.
That's shared pointer that I need to copy. Okay. Well, what I'm saying is, let me see if I can actually bring you example for the shared pointer. So where was I? I think this is the one, if I recall correctly. Okay, so this is the same employee thingy that we had. Let's minimize that. Now I have a shared pointer for it. Okay, so I'm saying shared pointer new employee yada yada. Then I'm creating that, and it was R is equal to whatever, and R print, and so and as you see, this R is actually another one. Now you're saying, what if now tell me what you were saying.
So I was saying, what if we do line 31,
Mm-hmm.
but do it twice? But that's because the new is going to create a new object, right?
Yeah, so
what if before the line 31, we set the new to another pointer and not that instead of.
wait. Just want to make sure that they're not the same. Okay. Yeah, well,
So
and I cannot call it P, I'm going to call it P2.
what if, because these two new are different objects, right? So they
Yes.
have two different memory location. What if you take this thing and then go above it and then give it like a employee pointer?
So
First,
you
and then
just
you
violated the law of using smart pointers for dynamic memory allocation.
Yeah. So
You're telling me, what if I create a pointer PTR equal to new and put those pointers in both of them?
Yeah.
Then you're screwed.
But you could do that, but it's just not wrong to do.
Yes, it's
Okay.
wrong to do it. That's why we have, you'll see, it's called make pointer. You actually,
Make pointer.
you'll see, yeah, I'll show it to you. So you don't actually do new. You say P is equal to make shared pointer. We'll talk about it soon. Okay, yes.
I didn't understand the destructor behavior fully. Like, I understand at the end of the life of.
Are you talking about shared or unique?
Kind of both.
Both?
The destructors.
Easy. If it's both, it's easy. Where is P created?
Right.
Test one.
This one, yeah.
So when test one ends, P dies, right?
Yes. Yeah, it dies.
And it's destructor, whatever it's pointing to, which is new employee will delete. So
But
it
is it the what was the virtual keyword doing there? Is it to
Virtual is my rule that I always say that when you create a destructor, make it virtual in case somebody wants to create their own more advanced smart pointer out of this one.
Like a child.
And so you create your own smart pointer out of my shared pointer that does even better, fixes those scenarios, okay? Something like that. And if you want to do that, then you want to make sure when it deletes, it actually calls the proper destructor. If you don't do that, it won't. The data will not get deleted.
And
So virtuality essentially guarantees that the destructor is always called, no matter what.
for that type or
For that object.
and okay. And for shared pointer, the
Wait.
wipeout.
Wipeout,
How does it repeat? How does it know to repeat for the amount of pointers?
it just counts the counter. If the counter is 0, it deletes.
Oh.
If the counter becomes 0 in wipeout, it means I was the last. Then everything's deleted.
Okay, and then we're good.
Yeah, and then we're good. So that's essentially what the wipeout did over here. So the wipeout of mine in here essentially says if the pointer exists, reduce it by 1. Then if the pointer exists and it's equal to 0, it was just reduced by 1. It means now you have to delete everything. But if the pointer was null, it means it was a blank thing. It was never pointed to.
But naturally, at the end of the program, it will come to 1, and then the last wipeout will
Yes.
finish.
So essentially, the destructor over here is called, it says, that's why I'm calling it conditional delete. My wipeout is I should have called it conditional delete. You want me to do that? Yeah, so with this wipeout thing, essentially what it does, the destructor is called and the wipeout checks. Am I the last one? Yes, let me delete. Okay. I know, it's,
A little nitty gritty.
yeah, yeah. But the funny thing is that this is the lowest population of people that I had in class and highest number of questions that are, which is very nice. I'm happy. Okay, this is good actually. I'm happy. So that's that one. Anyway, so yeah, so let's call this one shared pointer. SHPTR tester. Okay. So what was I saying? I was talking about. So the syntax of a unique pointer is exactly the same thing as this one. No difference. It works the exact same way. So this is unique pointer, and you have to include memory, but because it's in there, right? And that's that. So as you see, it says PTR new in 42 exclusive ownership of int, and works the exact same way. Okay, so actually I put over here, I overloaded void pointer. It's actually get in real one. So that was a bad example. I should have called it get, but get is the one that actually gives you the address. Okay. Yeah, so modify safely. And so this is essentially, yes.
Could you overload the ampersand symbol instead of like
We did.
const void to get the address?
That's wrong. Because address of PTR should tell you where the PTR object is located at, not what it's pointing to.
Isn't that
If you have, I'll answer to you in 2 seconds. If I have integer pointer p, then I write ampersand p. What does it mean?
the address of P?
Yes, which is a pointer to a pointer. Address of p becomes address of a pointer, and therefore it's pointer to a pointer, right?
Is it? No, no,
Oh, wait.
Isn't that?
Wait. Integer pointer p, integer pointer q equals to address of p.
But this is not like.
This is exactly what you're doing. You are saying, I want the address of P kept in Q. So you're extracting the address of PTR. It has to be address of PTR, not what it's pointing to. The address of.
Oh, right. Oh, all right. Okay.
So overloading is wrong. Because it's wrong, I never even thought about doing it. If you overload that ampersand thingy, you are making a mistake because an ampersand is supposed to, the address of operator is supposed to give you an address of an object. If you want to extract the address of the PTR unique pointer, that's your choosing, you can do it. Which is a crazy thing to do, but sure, I'll pass it always by reference.
So PTR get is not the address.
No, PTR get is the address of what it's pointing to.
Okay.
It's the raw address, let's put it like that. Oh, okay, so. I thought, I was so silly, I thought we'll actually go to parallel processing today, but what's the time? It's 40, holy moly, I cannot even teach this one. Okay, quickly, create unique pointers are like this. So this is unique pointer. By the way, you have a quiz, PGH. You have a quiz the next day you are coming in. I'm gonna create a compound type. I'm gonna tell you there's a file. I haven't designed it yet, but this is essentially what's gonna be. I'm gonna give you tell you there's a file with the binary records of that thing, and I'm gonna ask you to do stuff like give me the 10th record in a file, give me the last record of the file, print all the content of the file in reverse order, things like that. So you do fseek and fg and stuff like that. Okay. So it's essentially about accessing the data inside a binary file, going back and forth using. Shared pointers. Okay. There we go. Look at this. You see that? So you don't use new. You do make shared. Okay, you simply say auto, whatever, make shared int 25. So it creates a dynamic integer with 25 in it and gives it to you. So if you want to create an employee, you say make shared employee, and then you put the arguments of the employee in there, and it's gonna create it for you. So wow, thank you. 5 minutes left in your meeting. I love that thing. I don't know where it came from, but I'm a happy person that I heard that. Okay, so yeah, so shared pointers work like this, and then you can, as you see, you're processing, you're doing all this stuff, and you do another share. This is essentially a copy constructor, as you see at line 19, and at the end, one by one. So because it's in a block, the sp2 will die at the end of the block. I open the anonymous block over here, and so sp2 dies over here, but sp doesn't die. So if you actually use count, use count essentially the count I wrote. How many do we have? This is the same thing. So it's going to tell you, and then at the end, the sp dies and it wipes out everything. But that's essentially shared pointers that we have. And that's it. I'll go through the rest of the things. So we know what smart pointers are. Please go and study what we have in a smart pointer thingy. There's no questions in a quiz about smart pointer, but the next week you'll have quiz. I'll try to have lots of small quizzes done as much as I can every single time you're coming, so that file thingy that you're going to come and do next quiz, I'll try to make it small and do two things in it. Maybe pick up something like show me first, show me last, show me something in the middle, and print everything backwards. See if you can do it, okay? So remember this thing, beginning, end, anywhere, backwards. Questions? All right. Have a good one. Quickly close this so I can run to the other class.
I don't think I can take the quiz anymore, can I?
You-
Like,
We'll see.
I don't think I
No, no, we'll see if not, afterwards I'll provide you with a PDF of it
Oh,
to see what it is. Is that good enough?
sure.
Just you have to let me know, right?
Yeah,
Okay.
I'll be there.